Okay, awesome. Perfect. So yeah, thank you for the invitation, first of all. So today I want to talk a little bit about how graphs and how graph neural networks in particular can help us for multiple object tracking, and why using graph neural networks is the natural thing to do to solve this problem. So I'm going to start with a little bit of an introduction, since I know the crowd is not only multiple object tracking fans. So the multiple object tracking problem is the one where you have a series of frames in your video, and given this video, you want to find out which parts of the image depict the same object in different frames, right? So you want to end up obtaining trajectories that look like this. They could be represented by bounding boxes, they could be represented by segmentation masks, but at the end of the day, the hard problem is to actually connect these boxes across time so that they depict a coherent trajectory. Now, one might ask, well, why do we actually need tracking, right? So the first question, and especially coming from detection people, is why do we need tracking when we have detection, right? So it turns out that at some point, detection is going to fail, right? So one mode of failing is an obvious one, where the object is actually occluded. But there are also other failure modes, which include viewpoint variations, pose variations, blurring, illumination variations, that actually allow to detect the object only in a few frames of the video. And you can have also, for example, background clutter, right? But at the same time, one needs to perform tracking, and especially multi-object tracking, because we want to understand and reason about the dynamic world, right? We want, for example, to be able to predict the trajectory of a person that is crossing the street in case of an autonomous car, for example. And for this, we need to properly understand the past trajectory, which means that we need to perform object tracking. Now, in the literature and in the community, tracking has been posed as many things, right? It has been posed as measuring similarity, as correlation, as correspondence, like most problems actually in computer vision, also as a matching problem or a retrieval problem. But today I'm going to use mostly the formulation of data association. Now, tracking is also, for example, learning to model our target, learning about the appearance of our target, how our target looks like. And for this, there are sort of subfields and subcommunities that have been working on single object tracking or on re-identification, which focuses heavily on appearance. And the second thing we need to learn to model our target is motion, right? We need to make predictions of where the target goes. We need to learn how it moves. And for this, the community of trajectory prediction is actually very strong in learning motion, in learning interactions between objects. But let me go back to that formulation of data association. Why do I pose tracking as a data association problem? Well, this comes from using the paradigm of tracking by detection. So tracking is such a huge problem that we tend to break it down in two parts. We tend to use detections as input, right? So these are our proposals, if you will. And then what we have to do is we have to associate these detections in time in order to obtain full trajectories. So you see here that I've represented trajectories as just color-coded bounding boxes. So if two bounding boxes have the same color, it means that they represent the same person, the same trajectory. And so association, for this talk, I want to kind of break it down into two types of association. One is short-term association, which is the frame-by-frame association. And this is usually done with, tracking by regression or tracking by attention. So methods that essentially predict what is going to be the position of the object in the next frame. So it performs this short-term association from frame to frame. And this is usually the case for online trackers. Now, of course, they are very fast. They are very good for real-time applications, but they usually lack robustness under occlusions. And for this, people have worked also on what we call long-term association. So what happens when I actually want to fill the gap of, for example, this blue trajectory where we have this frame in which the person appears, then all the other frames in which we have no evidence that the person is there, and suddenly it reappears here a number of frames later. I need to connect these two detections. I need to perform data association, but this is not really short-term data association. And for this, I have to come up with different methods. There are the ones that are used in long-term association. Now, one type of long-term association that has been used already since, I think it was something like 2007, when it was introduced, this formulation, is graph-based association. So what I'm going to do is I'm going to pose the tracking problem as a graphical model, where the nodes are going to represent my detections and the edges are going to represent possible trajectories. So in this formulation, a trajectory across the video, for example, this red trajectory, is going to be represented by a series of connections, a series of edges that are going to tell me that these two red detections are actually connected. They actually belong to the same trajectory. And so I'm going to do the same with all the objects in this video. And in the end, what I'm going to obtain is these three trajectories across the graph that represent the three trajectories of the objects in the video. And so just as a little bit of a vocabulary, because I'm going to use this interchangeably, before deep learning, we used to solve this with classic optimization. And so we used to work with network flows. This is where this word flow comes in. So a node represents a detection, an edge represents a trajectory, also represents a flow in this vocabulary of the optimization that we're going to use. And in this case, one unit of flow is going to represent one pedestrian. So let's see what this unit of flow really means. So in order to find the trajectories in this graph, we're going to solve what is called the minimum cost flow problem, which essentially means determining the minimum cost of shipment of a commodity through a network. Now, in our case, the commodity are the pedestrians, right? So one unit of flow means one pedestrian. And we want to find the minimum cost of shipment, which means the optimal route to send this pedestrian from the beginning of the video towards the end of the video, right? What is the optimal path for the pedestrian to follow through this graph? And of course, the cool thing about this is that I'm going to find the solution for all three pedestrians at the same time. So it's not like every pedestrian can choose the path independently, but I'm actually going to find a solution that satisfies all three pedestrians. So I can send all pedestrians from the beginning to the end of the video. Now, of course, this is an optimization problem. So we're going to be driven by the objective function, which is a minimization function. And actually, what is going to drive the tracking is this term Cij, which is the cost that I'm going to assign to an edge. So how do I actually define this cost? So remember that we have in front of us a minimization problem, which means that if two detections belong to the same person, I want the edge between these two detections to be active. I want this trajectory to be created. And so since this is a minimization problem, I'm going to assign a very, very low cost to the edge connecting these two detections. So low cost is good for a minimization problem. It means that it's probably going to be used in the final solution. What happens when I have two detections that don't belong to the same trajectory? I'm going to want to assign a very high cost to the edge connecting these two detections, indicating the objective function that I don't really want this edge to be part of my solution. Now, the other things that one needs to know is that we have an indicator function, which is going to become very useful later, in which if an edge is active, so if it's connecting two detections and creating a trajectory, I'm going to assign 1 to this indicator function. If an edge is not active, I'm going to assign 0. And this is how I obtain the optimal set of trajectories. Now, everything that I've presented so far is a pipeline for graph-based association in which we extract detections, we compute some usually handcrafted features, and we assign them to costs in the edges. And then we run our optimization problem to obtain the trajectories. There is absolutely no machine learning involved in this pipeline. So as you can imagine, there's a lot that we can do in this space to improve things and to try to learn more and more from data. So the first thing that one can do very obviously is actually to learn the cost, right? Why should I handcraft the cost that I'm going to assign to an edge? I'm just going to take two detections. I'm going to put some geometric cues in there, and I'm going to let a neural network decide what cost should I put on that edge that connects these two detections. Now, one hopes that if these two detections don't represent the same trajectory, the cost is going to be very high, while if the two detections actually represent the same trajectory, the neural network assigns a very low cost. And this is basically the loss function that I'm going to use to train this neural network. So this is cool, right? We obtain more robust trackers, etc. But I still don't like that we have this feature extraction, which is now learned, and we have this optimization, which happens after it. This is actually not learned, and it's actually completely independent from the feature extraction. So the bad thing about this method is that we're not really learning the features in the right domain, right? So the domain for optimization is the graph domain, but the way that I learn my features is not taking into account this graph domain. So this doesn't sound right. And there's so much more that we can do, maybe unsurprisingly, using graph neural networks, right? So now that we know how to cast the mode problem into a graph, we can use graph neural networks in order to learn features directly in the mode domain. So here I'm representing, as always, my input detections and the graph that I've created with these input detections. And now what I need to do in order to use graph neural networks is to define some embeddings, right? To define node embeddings, which are simply a tiny CNN that takes in the input image, the input detection, and computes the feature embedding from that. And the edge embeddings. These are slightly more complicated, and we do have a tiny bit of handcrafting in there that we're improving in subsequent papers. But essentially what we want to encode in these edges is a ton of geometric information, so relative box position, relative box size, the time distance between detections, and also some appearance in there. And by appearance, I mean the difference of appearance between the two nodes that the edge is connecting. Some kind of re-identification, if you will. So now I have my initial embeddings, the node embeddings and the edge embeddings. And now what I can do is I can let the magic happen, right? So we use message passing networks, which essentially propagate these node and edge embeddings all over the graph, right? So what these methods do is essentially they have a series of message passing steps in which nodes communicate with edges and edges communicate with nodes. So you can imagine that after n message passing steps, if I'm a node that before any message passing, I was only aware of the own appearance of the detection that I represent, now after n message passing steps, I have a view of my neighbors. I have a view of what kind of other detections are out there. Is there, for example, a detection that is 5 frames away that looks exactly like me? This is now an information that I can have thanks to these message passings. And so this is really cool, right? Because now my embeddings, my node embeddings and my edge embeddings are going to be updated, but they're going to be updated exactly with the information I need for tracking, which is sort of a higher level information about what is happening in the neighborhood of the node. And so after this series of message passing steps, which are of course learned, now the only thing I need to do is basically solve a classification problem, right? Is this edge active or not? And this is what's going to give me directly the trajectories. So essentially my loss is going to be a classification loss. Is this edge active or not? But of course, like before I did this neural message passing, an edge, in order to say, am I active or not, it only had the information of the nodes that it connected. So it could say, you know, do these nodes look similar? Do these two detections look similar? Sure, you can have some kind of appearance information. Are these bounding boxes far away from each other, for example, for some position information? But after a series of message passing steps, I have now a much broader view of the problem, right? If I'm connected to this node, are, you know, 3, 4, 5 nodes in the future, am I still going to have connections that have, for example, a similar appearance? So is there going to be continuity to this track, right? Imagine like the power of this for tracking, right? This is exactly why we want to have this formulation and why message passing is so powerful for multi-object tracking. And so after classifying these edges, I obtain my trajectories and my job is done. So this is all great, right? And what I particularly like about this formulation is that now instead of having, you know, separate feature extraction and learnable and data association, since now the data association is learnable, I can actually backpropagate through the whole thing. So I'm actually extracting features that are good for the mod domain, which is in this case expressed with a graph. Now, I'm only going to show this one result because I really like this. It really shows the power of message passing for tracking. So in the x-axis, we have plotted the number of message passing steps. And in the y-axis, we have plotted two accuracies. On the left, MOTA, and on the right, IDF1. These are two metrics that we commonly use in tracking. And we see here the jump in performance that we have when we go from 0 message passing steps to 2, right? So this is only an update step from nodes to edges and from edges to nodes, right? So the only thing that we did is that I as a node have talked to my neighboring nodes and I've seen what is around, you know, do they look the same appearance-wise? Are they close to me distance-wise, etc.? This exchange and collection of higher order information from neighboring nodes makes a huge difference for accuracy in tracking. And you see that after that, you still keep improving things, but this first step of collecting information is when things really happen. So I think this is really cool and really motivates the use of message passing networks for tracking. Cool. So I've started this talk by saying we want to use this for long-term association, right? And I can say, sure, you can take 25 frames, create a graph, solve the graph, and we have solved these occlusions of up to 25 frames. And you're like, look, Laura, this is not really long-term association, right? I'm talking about 100 frames, 500 frames, 1,000 frames, the whole sequence. And then I say, whoa, this is a huge graph, especially if you start connecting everyone with everyone. If you start, even if you do some edge pruning, you're still going to have a huge graph that it's going to be hard to fit into memory. But most importantly, you're going to have a huge problem of imbalance between active and inactive edges. This means that you're going to have a lot of edges that are going to have to be labeled as inactive and just a few that are going to be labeled as active. And we know what happens when we have this kind of imbalances, right? The active edges don't have any effect on the loss, and it's really, really hard to learn in these conditions. So how can we actually make this scalable to 500, 700, 1,000 frames? Well, we looked back at the literature and we said, hey, you know, most of the trackers are actually hybrid, right? So they have some sort of short-term processing, you know, tracking frame by frame. And then they also have, in parallel, another type of processing for long-term occlusions, right? And you usually don't really write this down, right? You find it somewhere hidden in implementation details where it's written, oh yeah, we use a re-identification model to solve long occlusions, done. And it turns out that when we analyze the literature, we found that actually all trackers are hybrid multi-level trackers. But each of these processing, short-term, long-term, even mid-term sometimes, they are different, right? So every processing is engineered per level, right? There's a type of tracking for short-term, another type for long-term, different hyperparameters, completely crazy and completely non-scalable. So what we actually want to have is a unified hierarchical tracker where each tracker, short-term, mid-term, long-term, is the exact same tracker, so that it's highly scalable and it's unified and not really engineered for each particular level. Now, what do I mean by a hierarchical tracker? I mean a tracker that takes 5 frames as input. It finds the tracklets for these 5 frames. And then you go to this next level and you find tracklets for 25 frames. And you go to the next level and you find tracklets for 75 frames. And you keep growing and growing and growing until you reach the whole sequence, if you will. So this is essentially what we propose, a delicious and yet very strong tracker, which we name Sushi, for a strong, unified, scalable, hierarchical multi-object tracker, which essentially is going to take our input frames and it's going to create trajectories in a hierarchical way. Now, the cool thing is that we can now process really long clips, which is something that one cannot do with a monolithic graph, as I've explained before. So now we can process long clips of 500 frames. We can solve occlusions up to 500 frames. And we have the exact same graph neural network architecture and weights for each level. So really a general tracker, we don't need to engineer each level. And also the cool thing is that it generalizes, right? So as much as I love Mod Challenge and working on Mod Challenge for obvious reasons, we also want to generalize to other data sets out there. And so we tried on 4 diverse data sets and we have consistent state-of-the-art results by a large margin. Now, as I've said briefly, how this works is by creating tracklets which are increasingly long in time. So we have the first Sushi block, which is essentially the graph neural network that I've explained, which takes detections, it expresses them as nodes, and then solves the problem to obtain trajectories. Now, at the second level, things need to change a little bit, right? Because your nodes no longer represent detections, but they represent tracklets. Now they represent tracklets, which are the solution coming from the previous Sushi block. And so now your node is going to represent a tracklet, but you're still going to have the exact same graph neural network that is going to solve the problem and connect these tracklets into even longer tracklets. And you do this for several levels until you obtain full trajectories. Now, as I've said, one of the cool things is that we're not going to have 9 Sushi blocks, each with their own weights and, have this huge model, but we're going to have exactly the same architecture, exactly the same weights that are shared at each hierarchical level. And so what is cool here is that we have a model that is not really huge, but that at each level is going to learn which features to use, right? So intuitively, when I think about it, if I think about short-term association, I'm going to look more at position, right? So objects don't just fly from one part of the image to the other, but they move rather slowly from frame to frame. So position is a very strong indicator for short-term association. For long-term association, on the other hand, the object has been occluded for a while. It could be anywhere, right? Position is not a strong cue, which is why we usually rely on appearance, right? We rely on re-identification. And so the GNN, what it's going to do is at each level, it's going to choose which features to use, right? Depending on what works best at each hierarchy level. And this is not something that we have to choose, but actually the model can choose on its own. So again, a little bit of an overview of the pipeline. We have our detections as input, right? So this is still a tracking by detection method. We have our sushi block, which acts at the first level on just 5 frames. And from these 5 frames, we obtain the trajectories. Now, once we have these trajectories from frame 1 to 5, from frame 6 to 10, from frame 11 to 15, what we have now is another sushi block that takes these 3 outputs and tries to connect these tracklets among themselves to see how many trajectories can we get from frame 0 to frame 15. And we do this in a hierarchical way, right? Slowly, for 5, 25 frames, 50, 150, we keep growing and growing and growing until we reach 1,000 frames, or how many frames you need. Now, let's look at some ablation studies to see, like all this hierarchy, like how important is it, right? So I really like this experiment because it clearly shows how powerful it is to have such a hierarchy in tracking, and especially in graph neural networks. And so here what we're going to plot is in the x-axis, we're going to have the hierarchy levels. So one hierarchy level is essentially a monolithic graph that takes in the whole input and solves for the trajectories, and that's it. 3 levels is going to be, for example, 5, 25, and 512. And you go all the way up to 9 levels. And here on the y-axis, we're going to have the clip size that we're going to work with. So clip size of 8 means that I'm only going to be able to solve occlusions up to 8 frames. Anything else, I cannot solve for these occlusions. Of course, what we want to reach is something like 512, for example, which means taking in the full sequence in, so that if a person appears in the first frame, then it's occluded for the whole video and then reappears in the last frame. I want to have an edge connecting these 2 detections. I want to have the possibility of connecting these 2 detections if indeed it's the same trajectory. So with one hierarchy level, first of all, the first thing that we see is that it doesn't fit into memory to create a graph with one hierarchy level that connects the detections at frame 1 to the detections at frame 512. Even if you do edge pruning, it doesn't fit. But even if it would fit, learning in these conditions is really hard. So you see how we obtain this IDF1 accuracy for clips of 8, pretty much the same for clips of 32, but things start to get worse as we increase the clip size. And this is because of the imbalance problem that I told you about before. There are so many edges that should be labeled as inactive that it's really hard to learn about those few active edges, right? So the training signal there is just too small. And we try to have solutions in the loss function to balance that, but it's still too much of an imbalance problem. Now, what happens when we go to hierarchy level 3? First of all, we see an increase in performance across levels. So in general, it just works better for the same clip size. But the most interesting thing is that the performance keeps increasing as we increase the clip size, which was not the case for the monolithic graphs. So now we have a solution where we actually improve results as we increase the clip size, which is what we would hope, right? If we have a larger clip size, we can solve for larger occlusions, we should have better IDF1 performance. And indeed, we see that the top performance happens for clip size 512 and 9 hierarchy levels. So this is actually 13 points in IDF1, right? 13 points that we have gained from going from monolithic graphs all the way to this hierarchy of 9 graphs. So I think this is really a huge boost in performance. Now, let's see some qualitative results just to understand what is happening here. So at the level 1, as I've said here, we're dealing with maybe 5 frames, and we're finding tracklets in these 5 frames, which means that every 5 frames, our identity is going to change because the first 5 frames and the second 5 frames are not really connected, right? These are 2 different graphs that have been solved. So you see all the colors here flickering because these identities are changing every 5 frames. At level 3, we can see some more consistency, right? So tracklets get longer and longer, 25 frames, right? Things are pretty much stable when we go to level 6 or very, very stable at level 9, where we can really obtain these very, very long trajectories, and we can even fill gaps across 500 frames. So as far as datasets go, as I've said, we don't want to focus only on mod challenge, right? So we work on mod 17, which is kind of the standard dataset of mod challenge. We also work on mod 20, which is this crazy dataset in which we have more than 100 objects per scene. So you see here the level of proudness that we're working in. And this is, of course, also a problem for graph trackers, right? Because we need to create a graph that contains all these people, right? Each detection is going to be a node for us. And so it is also a problem memory-wise. And so what's going to happen is that for monolithic graphs, we can only solve occlusions up to maybe 20, 25 frames, right? Which is very, very limited. So this shows another powerful benefit of having hierarchical tracking. And then we also tried another datasets, like, for example, dense-track that contains more abrupt motion, or BDD that contains car tracking, so that we have completely different features and we still show that our method generalizes. Now for some benchmark results. So I think a cool thing here is that we are improving results not by a little bit, but by a really large margin, which shows two things. First of all, of course, that the formulation is very powerful, but also that there are really long occlusions that nobody has really targeted before, right? On some data sets, we have an increase of almost 10 points in IDF1. This is a huge, huge improvement and shows really that there were many occlusions that people were not even trying to solve because they are really long occlusions and it's really hard to connect these dots without creating false trajectories, without creating a lot of trajectories that are not really there. And as you can see, the improvement happens all across the board. Okay, so I want to leave quite some time for discussion. So what I've presented and hopefully convince you of is that graph neural networks are actually really powerful and robust trackers. They are capable of adapting to short and long-term association challenges, which is perfect because now we don't need to engineer every bit and piece and put some features for short tracking, then some features for midterm tracking and some others for long-term tracking. We just put everything in there and the neural network is going to learn which features to use at each time. And in case you were wondering if you can do 3D tracking, if you can do online tracking, the answer is yes. And we had a paper that was presented last year, which is called Polar Mod, that explains exactly how to use this kind of graph neural network formulation and use it for LiDAR tracking. And the cool thing about that is that we use only geometric relations. We didn't use any type of appearance. And we show that the tracker is so robust because of this graph formulation that if we obtain state-of-the-art and we actually generalize to other data sets. We generalize across LiDAR sensors, we generalize across locations, because we use only this geometric information and a really robust graph structure for tracking. And the other cool thing about Polar Mod is that it's actually online. So we show how this tracker that I've presented right now, which is basically an offline tracker, right? So it takes the 1000 frames, it solves the trajectory, and it gives you the trajectory for all 1000 frames, right? So it's not really online. While if you want to have an online tracker where as soon as a frame comes in, you process it and you obtain the position of the tracks in this new frame, and you keep going as soon as the frame comes in, you can still do this with graph neural networks, right? And we show in that paper how to adapt the tracker in order to make it work online. So if you're interested, also check it out. Now, I do want to say that this paper, the sushi paper, is going to be presented at CVPR. I have omitted many of the details, but if you're interested, go check it out. Go talk to Orchon and Guillem, who are both authors that are going to be present here at the conference. So with this, thank you very much for your attention, and I'll be happy to answer any questions you have.
Thank you, Laura. Maybe we can start with one questions because some questions are questions.
So I have to say that I don't hear you really well when you talk.
Okay. There are some questions from the chat, so let's first look at that. Sorry.
So the question is, how do you obtain or generate training data or entries? You can
Right
in the chat if you don't understand us, and I will try to fix that.
Yes. So, okay, the question is, how do you obtain or generate the training data or ground truth? So for my challenge, this was a fun postdoc time that I had where I was labeling manually a lot of sequences, and I'm not joking here. So of course, there's a lot of manual work in labeling these sequences, and most of the sequences that we work with are manually labeled. Now, a cool thing that we're starting to do now is we're starting to use offline trackers, right? So trackers that are more robust, like the one that I've presented, to label sequences to train online trackers, right? And I think this is really cool because there are just maybe a few cases that offline trackers cannot really resolve nowadays. And these are the ones that you can actually tell an annotator to solve. So this is something that we're working on, trying to use this for auto-labeling, trying to improve the labeling pipeline so that, someone doesn't need to spend their postdoc time labeling more challenge sequences. I can go on and read the questions from the chat.
Yes, that sounds good.
Okay, awesome. So someone says that sushi depends on detection results to work. Are you considering integrating detection as part of the pipeline to make the whole solution end-to-end? This is actually a great question. So for now, sushi is a tracking by detection method, which indeed it means that the tracking step and the detection step are completely independent. So we are thinking into how to integrate detection as part of the pipeline. But of course, you need to create the graph from something, right? So you could create the graph, for example, from proposals instead of detection. So then you would have more nodes and you would need to decide between, for example, 5 proposals that represent one object, which one shall I choose? So it's not only one detection per object anymore. So it's a bit of a different formulation. But so far, we haven't found a way of doing this end-to-end. So in order to work in an end-to-end fashion, I would recommend checking, for example, our tracker TrackFormer, which is based on transformers, which are essentially graph neural networks, right? And there indeed you have the detection and the tracking step completely coupled, right? So for each frame of the video, it's going to tell you where the objects are, whether these are new objects or these are already tracked objects. And there's a transformer that it's going to do this frame by frame. So this is an online tracker. So that's also a really powerful tracker. I have to say it requires a lot more data to be trained. So as anything with transformers, lot of data helps. Otherwise, results are really not the best. So of course, there are pros and cons, right? But this is, I think, the closest that you can get to a real tight integration between detection and tracking. Okay, then there's another question by Kevin that says, have you tried this with distant or small objects? For example, 5 or 20 pixels per detection. I don't think we have those type of objects in Mod Challenge. I think the threshold for the objects is actually larger, for which we just cut objects and do not evaluate that. I could imagine that if we do have a detector that works for that size, then graph should be a good option for that. Even if, for example, the appearance information would be bad because there's not much appearance that you can get with 5 pixels. We showed in Polar Mod that we can use only geometry information for tracking. And the actual formulation is very robust because you have this graph that solves for all the tracks at the same time. And so it could also work for these small objects. The question is more if there's any data set that has them annotated, but I imagine that it would work, yes. So I'm just going to read the third question from the chat. So it says about the 3D case, what is the form of the data? Voxels, 3D points, meshes, or another form? So in our case, we use 3D points. So we use the LiDAR output. And then we have a detector on top, a 3D detector. And after that, it's exactly the same as sushi, or in our case, we use monolithic graphs still in that work. But once you have the detections, then it's really the same formulation. So it really depends on the tracker. Okay, so a question from the audience, I assume, can these graphs be used for multitask objective for long-term video understanding? Ooh, that's a great question. I think so. So my goal would be to represent any task in dynamic scene understanding with graphs, right? So we have seen like scene graphs, like there's a lot of work on scene graphs. There's work on representing interactions between objects with graphs, right? So I think it's really a great representation to just distill in general interactions between dynamic objects from, you know, one frame to the next, which is the case of tracking, from dynamic to static objects, which is more the case of